In this lecture, we are going to analyze the classical structure of the spinning electron. It's part of the general formalism for describing classical spinning particles, and let us see how the electron is described. In the relativistic free case, when the kinematical variables are time, position, velocity, and orientation, which is the most general case, we are going to analyze this manifold, but with the constraint that the absolute value of u is c. So, what we are going to analyze is such kind of particles for which the point where they are located are moving at a speed unreachable for every inertial observer. What we see is that this manifold is also a homogeneous space of the Poincare group. Given two sets of these values with this constraint, there is a group element, a Poincare transformation, which links them. So, this manifold can represent the kinematical space of a classical elementary particle. But if u is equal to c, there are two possibilities. One is that the vector u is a constant vector. So this particle is moving in a straight line at the speed of light. This is the idea we have of a photon. But there is another possibility, the possibility that the absolute value of u is c, and therefore it has an acceleration, and velocity and acceleration are orthogonal vectors. This second possibility is going to be the classical description of the Dirac particle or the electron, and is devoted this lecture. Well, for this Dirac particle, consider that the general Lagrangian will be this. Once divide the capital tilde L0 over T dot takes this form, and therefore the netted constants of the motion, which can be built with this Lagrangian, where the only requirement is that the absolute value of u is c, are these 10 constants of the motion, where the spin s, the angular momentum with respect to the point r, takes this form. We have seen that in the previous lecture. Okay, now if you have a look at the kinematical momentum and the constant of the motion and the pure Lorentz transformations, we are going to transform this term in terms of this position vector, so that we can arrange these two terms together, and the kinematical momentum is written in this form: h r minus k over c squared minus pt. It has been embodied there. Or, if you like, this position vector r minus k I call q, such that now if I take here the time derivative, because this is a constant of the motion, I show that p can be written as the Hamiltonian times the velocity of the point q. V is the time derivative of the point q. The point q clearly represents the position of the center of mass of this object. Oh, but this q is different from r whenever k is different from 0, but k is different from 0 whenever the particle has a spin, and the spin is related to u and w. So whenever this more general particle contains these two extra terms we compare with the point particle case, the center of mass position will be a different point than the location r of the particle. Now, since p and h satisfy this invariant relation, introducing the expression of p, we get that the Hamiltonian, the energy, and the linear momentum can be written in terms of the velocity of the center of mass in the usual way, like in the point particle case, but we have a plus or minus sign here, because the relativistic formalism supplies two solutions. One, if energy is positive and linear momentum along the velocity of the center of mass, we call particle, and antiparticle in the other case, when the energy is negative and the linear momentum has the direction opposite to the velocity of the center of mass. We shall clarify the differences between particles and antiparticles in a future lecture. Now, the kinematical momentum in general takes this form, and if we take the time derivative of this equals to 0, which is the time derivative of this expression, we have seen that P is not along U, but if we take here the scalar product of this expression with U, because U squared is C squared, and separating the Hamiltonian, we see that this expression reaches this form. The scalar product with this is 0, and the scalar product of this is this one. Now we have a linear relationship between the energy and the linear momentum. This expression, when quantizing the system, is going to be transformed into Dirac's Hamiltonian. This is the expression of Dirac's equation from the classical point of view, because when we quantize this system, H will be replaced by the operator, like time derivative operator, H bar time derivative operator. P will be represented by H over I gradient operator, and U is these functions by the corresponding operators in terms of Dirac matrices, and this will give rise to Dirac's equation. Now, J is another constant of the motion. If I take the time derivative, I arrive to P is constant, but U is not a constant vector. So the time derivative of the spin is not a constant of the motion. This time derivative is orthogonal to the direction of the spin. So this object, the angular momentum with respect to the point R, is moving along its point. Its endpoint is moving along a plane orthogonal to the direction of the center of mass velocity, to the direction of the linear momentum. So the spin with respect to the point R is not a constant of the motion except if P is equal to 0. Well, what we can see when quantizing the system is that this dynamical equation is the same dynamical equation satisfied by Dirac's spin operator when written in terms of sigma Pauli matrices, and therefore the angular momentum with respect to the point R, with respect to what is going to be the center of charge, is the classical equivalent of Dirac's spin operator. Now let us define what we understand about the center of mass observer. Because K is written in this form and P is proportional to the velocity of the center of mass, well, that observer who measures K equals P equals 0 measures V0, P0 and K0, Q0. So for that observer, the center of mass is at rest and located at the origin of the reference frame. So for that observer, at the origin there is a point which is never moving, which is the center of mass, and the class of these observers who have these measurements of these two conserved quantities, we call them the center of mass observer. They are not uniquely defined. We have an arbitrary rotation and perhaps an arbitrary time translation. But for these observers, we have that nice feature. S is a constant of the motion for that observers, and P is 0 and K is 0. Then from the expression of the kinematical momentum for this observer, because this is 0 and P is 0, the energy for that observer is mc squared. I can separate position R in terms of the constant spin in this frame. Well, what we have obtained is the dynamical equation of the point R for the center of mass observer. Here is R, here is the time derivative of R. R is moving in a plane orthogonal to the constant vector S. If I take the time derivative of this, we get U is also orthogonal to the spin. So the point R, if I fix the spin direction, is moving in a plane orthogonal to the spin. If I make the scalar product of this expression with U, R cos U is 0, so the absolute value of R is constant. So the point R for the center of mass frame, once the spin has been defined, is moving along a circle of radius R0. Let us see how is this motion for the center of mass observer. For the center of mass observer, this is the dynamical equation, and we fix the spin in this direction. The point R is moving along this line. The radius is S over MC, and the center of charge, point R, is moving in this way because if you see the cross product of S times this velocity is along R. Now, if we had a motion of a mass along this trajectory, the angular momentum of this mass with respect to this point will be upwards, not downwards. So the spin related to the motion of the point R has an anti-orbital direction. But the spin, we know that has two parts, one orthogonal to the velocity u, and therefore this part z has to be perpendicular to that plane, so it is along the direction, and another w related to the angular velocity, which will be along the angular velocity, but this part must be larger than this part because the total spin is pointing downwards. Now the angular velocity of the trajectory of this point is c over 0, can be written in this form. Okay, this is what we get without postulating any Lagrangian. Now let us quantize that model. But we are going to quantize this electron in the center of mass frame. We know that this particle is a system of 6 degrees of freedom. 3 represent the position of the point, and 3 the angular rotation of a frame associated to that point. But in the center of mass frame, if we fix the direction of the spin, instead of 3 we have 2 coordinates moving on a plane, and as far as the orientation is concerned, we have just one angle, the rotation of that frame, which can be taken along the direction of the angular velocity. But the phase of this rotation is the same as the phase of the point on the circle. So we only have just 2 variables, the x and y variables, but because the point is moving along a circle with a constant velocity, of these 2 Cartesian variables, only one is relevant. The other is completely determined if we know the trajectory of the point. So what we finally have when analyzing the center of mass frame is that it reduces to a one-dimensional harmonic oscillator, for instance along x-axis, and of pulsation omega. So this elementary particle, when analyzed in the center of mass frame, has been reduced to a one-dimensional harmonic oscillator of pulsation omega. But omega is this one. But because it is an elementary particle, this harmonic oscillator cannot have excited states. If it cannot have excited states because it represents an elementary particle, it is a one-dimensional harmonic oscillator in its ground state. And therefore, because the particle is at rest, the energy is mc squared. Mc squared must be related to the energy or the harmonic one-dimensional harmonic oscillator in its current state, and when compare both expressions, the value of the classical spin is necessarily 1/2. The Dirac particle, whose point r is moving at the speed of light, is necessarily a fermion. Okay, we have described this Dirac particle by only using symmetry principles and without postulating any Lagrangian. The point r is the point where the external forces acting on the particle will be defined and thus represents the location of the center of charge. The spin of the particle is not quantized. It is unique. It takes a unique value in terms of Planck's constant. It is unique because the electron can never have excited states. So this internal motion is not modified. This angular velocity internal is not modified. So the internal angular momentum has this unique value. But this particle, which is localized at the point r, has another characteristic point, Q, which is interpreted as the center of mass. So if we have an object with two characteristic points and we have the angular momentum with respect to one, we can compute the angular momentum with respect to the other. So the angular momentum with respect to the center of mass will be the angular momentum with respect to the center of charge plus the separation cross the linear momentum of the corresponding reference frame. In the general formalism, we can express both spins similarly as the linear momentum and energy in terms of the position of these 2 points on the velocities of these 2 points in this form. Well, the most general Lagrangian will be this. L0 is the unknown, but not necessarily Lagrangian for describing this object, plus Li, the interaction Lagrangian. But the kinematical variables which appear here are the same as the kinematical variables on the interaction term. So the potentials which define the external forces will be defined at the point r. Therefore, the point r is going to be interpreted at the center of charge of the particle. Well, this formalism is written in this monograph, and you can also get these documents of a lecture course I lecture at the University of the Basque Country. You can contact me, and the final lecture will be devoted to the classical description of the spinning photon. Thank you for your attention.